All right, hi everyone. Welcome to Chapter 11's practice problem video. We are going to go over the practice problems from the book and from the PowerPoint presentation. If you've watched the lecture video already, you saw some of these, some briefly, some a little bit more in depth. But let's talk about what we're working on here. These are linear programming, meaning we are giving Excel a series of essentially programs that tell it what it can and can't do, and then asking it to find us a solution. So in linear programming, no matter what the setup is, we are always looking to maximize something or minimize something. In this problem, we've got a simple maximization problem. And what we want to get done is to maximize the profit. We want to make the most amount of money we can. We are a company making standard size golf bags, deluxe quality golf bags, and we want to make the most profit we can given the amount of limitations or constraints put upon us. And in this problem, the constraints are that of time. One of the biggest constraints on all of us, right? The amount of time we have available to do various tasks. So we are given the amount of time that it takes for us to do the various tasks that have to be done in order to manufacture one standard bag, one deluxe bag. And this is going to be true of all the problems. You're given a series of constraints in all of them. You're going to be maximizing or minimizing something. And when we are when we're setting these up, the first thing that we need to do in the setup is to formulate the problems. You'll see this is around page 543, 544 is where this problem starts. But problem formulation is talking about making sure that we can state the mathematical problem as a word problem. It helps us to understand it. It helps us to work through the problem. And that's what formulating it is. You're trying to figure it out and make into words what these mathematical formulas are going to look like. So what we do is we need to write out a few things. One of those things is what our objective is. Our objective, known as the objective function in linear programming, is to maximize this thing, this very explicit thing that we're trying to maximize, or minimize this thing, right? So in this case, the objective is to maximize the total contribution to profit, okay? Maximize total profit subject to the amount of profit contribution for each one of the items that we're making. And so what we're going to be doing in this problem set is part of it is going to be writing out the formulas, writing the formulation of these things, describing the objective function, describing each of the various constraints, defining the decision variables. Now, a decision variable, you're going to see a lot of variables, and you could come up with letters and abbreviations for things, but it's not a variable unless it's going to be included in your mathematical formula. And it's not a decision variable unless you can decide what that number is. So what I mean by that is if we looked at the amount of time that it takes to finish a standard bag, we see it's 1 hour, okay? So we might come up with a variable to stand for finishing time, but there's no need to, because we're not deciding how long finishing time takes. There's no decision there. Finishing takes an hour. That is a known quantity. That's going to be one of our inputs, one of our known parameters of the problem. Sewing time takes half an hour. Cutting and drying takes 7/10 of an hour, 42 minutes, right? Gosh, I hope that's right. However long it takes, those aren't decisions. Those are known things that exist. What we're deciding is how many standard bags are we going to produce and how many deluxe bags are we going to produce. So anything where we're having to decide how many to produce is going to be part of the maximization or minimization of the problem itself. So the number of standard bags we produce is going to lead directly to how much profit we make in total. The number of deluxe bags, the same thing. And so what we can do when naming the decision variables, often you'll want to just use a letter that makes sense, that helps you follow along with the problem. So standard bags, deluxe bags, S, D, great. You could do A and B, you could do X and Y, you could do X1 and X2. Whatever it is you set up for the decision variables is fine. What matters is that you then go on to define what that letter stands for. And typically this is more explicit of a phrase than this, meaning it doesn't just say number of standard bags, but number of standard bags to produce, number of deluxe bags to produce. Is usually more intricate statement than just what they have here in the book, but we'll go along with it. And then every time in a mathematical algebraic formula you see the letter S, you know what S means. It means the number of standard bags you end up producing. It's an unknown number, but by setting it up in a certain way and having all the parameters in place, those constraints in place, Excel will figure out what S actually is as a real number. Same thing with D. It'll find these and then it'll run back through the formula again to tell us our total profit contribution. So we're given some other information in this problem. We're told that we're going to make $10 in profit contribution. Now, think of profit contribution as the difference between revenue and costs, but on a per unit basis. How much is that one unit contributing to profit? So that's profit contribution. So we're making $10 in profit for every standard bag, $9 for every deluxe bag. So therefore, the total profit contribution is equal to this formula right here. 10 times S, so $10 for every standard bag. We know that standard bags is the letter S. So 10 times S plus 9 times D. And that means we're making $9 for every deluxe bag, because we know that D stands for deluxe bags in this instance. Our objective was to maximize the total profit. Therefore, we can write a simple objective function. And to me, this is a little more simple than I like, but max 10S plus 9D, maximize our profit. So we're using max as an abbreviation for maximizing whatever it is we're trying to maximize. And we're using 10S plus 9D to say that whatever the profit ends up being, we want S and D to equal the right ratio of numbers that it maximizes the possible solution to 10S plus 9D. Whatever that is, we want it to be the highest number on the outcome of that. So the next thing we got to write is all the constraints in terms of the decision variable. So for every amount of S or D that we produce, standard bags, deluxe bags we produce, we're using a certain amount of our constraint. So the hours of cutting and drying time used has to be less than or equal to the amount of time available. We can't use more time than we have available. With people we can schedule for that, hours were open, whatever the case is, we only have a certain amount of time available for this tasks. And so whatever it takes to do that task in time has to be less than what we have available, okay? So for the first constraint, meaning the amount of total cutting and dyeing time we used, we know that if we look back on our chart, that it takes, I gotta scroll back a page real quick for you, too far. We know it takes 7/10 of an hour to make one standard bag and 1 full hour to make a deluxe bag. So for this constraint, which we could just call cutting and dyeing time or total cutting and dyeing time, the label is important just to help follow along with it. But in this case, we could just write out 7/10 S plus 1D. And now I don't like this myself. I think I know I said in the lecture video, I don't like you using fractions here. I would much rather you put 0.7, right? Or convert it to minutes and then turn everything into minutes. This would be 42 minutes, right? 1/10 of an hour is 6 minutes. 6 times 7 is 42. That's how you get to 42 minutes, 7/10. So I don't like this formula, but we're going to, again, go along with it. I don't like, the fraction. It's just hard to visualize, but it's fine because once we put this in Excel in the actual multiplication we're going to use decimal places. We're going to do equals 7/10 in one cell, and that's going to do the math for us. If we're going to do a decimal place, so it's fine. So the amount we use is going to be equal to 7/10 of an hour for every one we produce. So if we produced, 2 standard bags, it would be 82 minutes. 14/10 of an hour. If we made 5 deluxe bags, it would take 5 hours. We add those together, and those have to be less than or equal to 630 because we have 630 hours available. So we're well within that. We don't have to use all of it. And often the optimized solution is going to leave some resources left over. I talk about what those resources are called in the other video. So make sure you look at that part of it. But we already do that for each one of them. So whatever the amount of time used times standard bags plus the amount of time used for a deluxe bag has to be less than or equal to that resource available. So in Excel, in our problem set, we have to write these things out. So we've got to do a couple things. First thing, we're going to say let S equal, you don't really have to write the let, it's just more proper. The number of standard bags to produce. And then we're going to write the same thing. Now I've got this set up as a merge cell. So let me just sidebar real quick. If you want to add a line and scroll down and within a merge cell, if you hit enter, it's going to leave the tab. And this is a little annoying, and I apologize, but when you're writing this out, instead of hitting enter, you need to hold Alt and press enter, and that's going to go down to the next line. You also can't tab to indent. You just need to add a bunch of spaces. So again, I apologize for that. It just is going to be the best way for this to work out as far as being able to view it for me goes. So not the ideal. Ideally, I would have you submit a separate Word document with these things in them. Or I would have inserted a text box for you, but it doesn't want to show up on Blackboard, and then people worry that it's not there. So this just is going to be the best way to set it up. We'll deal with the holding Alt and press enter. So again, I apologize. It's a little annoying when I was writing this out myself. So I know what you're about to go through by forgetting to hold Alt and pressing enter and going back into it. So that's going to be right here. We've defined our decision variables. The next thing we're going to want to do is we want to write our objective function. The objective is to maximize profit contribution equal to 10S plus 9D. And then we're going to write out all of our variables. And to save time on this video, I'm just going to copy and paste them from my cheat sheet, which is on my other screen. And it's subject to basically, I've already, where are these letters from? What's part C? Interesting. Pausing the video now. All right, so we've got subject to the amount available. So 7/10 of an hour for every standard bag, 1 hour for every deluxe bag. 1/2 hour for every standard bag, 5/6 of an hour for every deluxe bag. 1 hour for standard, 2/3 for deluxe. 1/10 for standard, 1/4 for deluxe. And all of these are going to be less than or equal to the amount of time we have available for each of them. So we've got cutting and dyeing time, sewing, finishing, inspection, and packaging. And then the very last one you always need to write in your formulation is that each of the variables, so just list all your variables separated by a comma, that has to be greater than or equal to 0. Now, if you're having trouble typing this this symbol here, that's fine. You can just write greater than or equal to like that. It just has 2 separate things, less than or equal to written that way. Not an issue at all. All right, so with this being formulated, and again, you're just kind of looking through the word problem and figuring out how many constraints do I have, and what are those constraints? What do they need to be equal to? less than or equal to, greater than or equal to. And these are set up as a series of left-hand side and right-hand side, usually abbreviated in certain text and in Excel, LHS, RHS for left-hand side, right-hand side. And so this is done. This formulation is finished. So now let's look at the way that this is set up for us to run our production. So we've got the amount and time. In this particular case, you're going to need to type in the equals 7/10, the equals 1, equals 1/2, just so it converts it to decimal form. It wouldn't really matter. You could just type in the decimals, except for the part where to get the exact number on 5/6, if you just typed in 8.33, it's not going to come out exactly right on this one. So I don't think this is going to happen. Yeah, I think it will actually happen on the regular problem too. So just any of the fractions, if it's 1, you go ahead and just type in a 1, that's fine. But any of the fractions, just write equals, and then this one's 2/3, so equals 2/3, just so that the answer comes out right. Otherwise, it's going to maybe be off by a unit, or find a different solution altogether if it doesn't round right. So all the fractions, just type equals and then reflect the fraction out, so it converts it for us. Equals 1/4. Okay, so we're done with that. And again, if it's the whole number, if it's a whole hour, whatever the case is, that's fine. You don't need to write it. You can just write 1 there. Okay. So, but in general, anything that I color in this like light salmon color right here, you're needing to do a formula in. Anything I write with this light blue, generally just going to be inputting a value. So I've already inputted these: 630 hours available, 600, 708, 135 hours available. And then the profit contribution per bag are right here. So these are just our parameters. This just sets up, this allows us to refer to these parameters when we do the model. So below that, we've got the model. And the first thing to know on these is this spot right here could be any number. We don't know the solution. Why did I just put 1 for each of them? Because we're going to have some formulas down here. And if I leave this blank and I refer to these blank cells, then we're not going to know if our formula is working or not. So the amount of cutting and drying time, or cutting and dyeing time we use, is going to be equal to the amount of bags of each type we produce times the amount of cutting and dyeing time for each of them, and then add it together. So if I make 1 standard bag, it's going to take 1 times 0.7 plus 1 deluxe bag would be 1 times 1. However many I make, I need to have that multiplied by the amount of time used for that many bags, and then add those two values together. Add the total amount used for making standard bags and the total amount used for deluxe bags. Now, what I could do is I could just write equals this times this plus this times this, and that would work. But if we have a longer series of constraints, we wouldn't want to type that out every time. We wouldn't want to click on all those ones and maybe misclick. Instead, we can use a sum product feature that we've used in past problems, and we just have to select both of our arrays. And because of the way this is set up with cutting and dyeing, sewing, finishing, inspection, packaging, matching these, what we can do here is we can say equals sum product, highlight these ones and lock them in, because we don't want that reference. The amount we actually produce, we don't want that to change. And then our second array we put right here, and it'll give us the sum product. Now again, this is if we just made 1 bag. We only put 1 here to see if this is working. If I don't put anything there, I'm just going to get 0, and I don't know that it's working or not. So I'm just putting these in as a placeholder. When we run solver, this is going to get solved for us. So we know that 1 times 0.7 is 0.7, 1 times 1 is 1, and 1 plus 0.7 is 1.7. So it's working. And then I can drag this down, and let me adjust the number of decimal places. There we go. Keep it standard. From here, we want to know one thing on this particular problem, which is how many hours do we have left over to know what we used up the maximum of. So This is just a simple one where hours available minus hours we used. You're going to need to know that for your problem. So just do hours available minus the hours you actually use up, and then it'll ask you how many hours were left over of certain ones. And then our profit, how much profit are we going to be making? Well, the profit's going to be equal to however many bags we produce times the profit contribution for that bag, plus however many bags of the other type we make times the profit contribution of that one. So once again, we've got to do a sum product formula here. So sum product of this one, because we don't have to lock it in, we're not dragging it down. So if I make one of each bag, I've made $10 and $9, and that's it. But not good enough, because we want to actually set this up to make some money. We want to make the most money we have, given that we have all these hours of time available to us. So let's set this up. We set this up using the data tab and then going to solver. And here's what we need to do in solver. The first thing we do is we set our objective function. Our objective is whatever it is we're maximizing or minimizing. In this case, we're maximizing our profit. So we click on profit right here. Next thing is make sure that you've got either max or min selected. This is a maximization problem, so we leave it on max. When you go to the next tab, it's going to default to these same things. You have to set it up again on the next tab. So if you had max on one tab, you're going to have max again. So you need to make sure you change it to min if it's a minimizing problem. By changing the variable cells, what are we changing? What variables are we changing? The only ones we can decide on. Those were the decision variables. So the decision variables are right here. It's however many we make. We don't know what we're making. Solver is going to tell us how many to make. It's going to tell us the exact amount to make in order to optimize this solution. Finally, we want to add some constraints. So constraints are set up as a left-hand and right-hand side. And because we formulated these, we know that all four of these are less than or equal to. Whatever's on the left side on hours used is all less than or equal to the hours available. Because that's the case, I can select all of these left-hand side. I can leave this set to less than or equal to, and then select all of these right-hand side. I can do all that together because it's the same direction. Now, if some of these were less than, some of these were greater than, I would have to hit add and then highlight the next series of them. And then maybe the direction reverses again, or there's an equal sign. Add and then add the next ones in. But anytime they're all going the same direction, they're all less than or equal to, then you can set it up in this manner. So we'll hit OK. And then always make sure this is on simplex LP for this problem. These other ones are for more advanced computations. And then click solve. And if it worked, it's going to say this: solver found a solution, all constraints and optimality conditions are satisfied. Keep the solution? Yes. Now, since I haven't finished writing your problem set, it's possible it may ask you to look at an answer or sensitivity report. If you need either of those things, you can just click on the reports before you hit OK, and it'll print it out for you. So I'm going to go ahead and click them both just to show you what I mean by that. So I'm going to hit OK, and it's going to create a sensitivity report for this problem and an answer report for this problem. Okay. But meanwhile, it found a solution for us. It told us to make 540 of these standard units, 252 of these deluxe units. And if we do, our profit's going to be $7,668. And we can see here, we had plenty of sewing time left over, plenty of inspection and packaging time left over. We didn't use all of it, but we still optimized our profit. So if we look on a sensitivity report or an answer report, we can see that the term binding constraints refer to anyone where there's no slack value. Slack value is how much did you have left over? So that's your slack value. If I just looked on this sheet, I know that I have 120 slack hours available for sewing, 18 for inspection, and then these ones that I have 0 slack available, those are binding constraints, meaning I can't change those in any way. I can't go up and still make the same amount of profit. Whereas I could reduce the amount of available sewing and it wouldn't change anything. So that's not a binding constraint. The sensitivity report tells us something about how much we could improve our profits if we were to add more time. So if we freed up some of that cutting and dyeing time and we freed up some of that sewing time we didn't need, and we made more time for cutting and dyeing, every extra hour we have available is worth an extra $4, $4.375 to us. Every extra finishing hour we have available is equal to another $6.93. That's true up to an increase of 192 hours, and then it stops being true anymore. Then you'd have to rerun it if you gained 300 hours available. The formula, the whole thing's going to change a little bit. Same thing here. Be liable increase and decrease, and have this shadow price still be true. Okay, so that's it. That's how to formulate a problem and write a constraint. So we're going to go to the next one, which is a very similar problem, except that there's a lot more constraints going on. So in this one, we've got the TV ads to run, and it's let me find this problem in the book. I'm going to pause real quick while I find this problem. All right, we're on I believe page 570. So in this problem, we're told that they're going to run an advertising campaign. They have various amounts of potential customers reached by running a daytime TV ad, evening TV ad, newspaper ad during the weekdays, a newspaper ad on Sunday, and a radio ad. We might reach this many customers. The cost per advertisement is this amount of money. The maximum amount of times available to run that each month is right here. Only 4 Sundays in the month. I don't know how we get to 25. It's a weird number. Exposure quality units. I'm not sure what that one is. That's some internal rating from the company, I expect. And so we've got on these problems a lot of wording to try to figure out what our constraints are. So decision variables, well, we can only affect how many ads to run. So we have to give a abbreviation to each of these. Now, I wouldn't have set this up with 3 letters for one variable. I just don't do that. At the point where I need 3 letters, because daytime TV, evening TV have to be 2 different, D and E might work, but then you've got daily newspaper for as DN, Sunday newspaper, so you can't use N here because then you've got a different type of newspaper. I guess you probably use D for daytime TV, E for evening TV, N for regular newspaper, S for Sunday newspaper, and then R for radio. That's how you could do it with 1 letter instead. But again, you could use X, you could use A, B, C, D, E, right? It doesn't matter as long as you define it. And then every time you see that letter or series of letters or letter number combination, you know what it's defined at, what that means. So additionally, you've got $30,000 budget. You have to have at least 10 TV commercials. At least 50,000 customers have to be reached. No more than $18,000 on TV ads. And remember, there's 2 different types of TV ads, daytime and evening. And 65 exposure quality units. So what am I maximizing? Okay, so we're actually maximizing our exposure quality, not the total audience reach. I see. We need to reach at least 50,000 customers. So that's going to be one of our constraints. Our maximized problem is going to be the exposure quality units instead, which, okay, that's bizarre. So we know that all of these, the amount of ads we can run are going to be our first 5. There's 5 different types of ads, and we have a certain amount of each one that we can run. So DTV less than or equal to 15, ETV less than or equal to 10, less than 25, less than 4, less than or equal to 30. So that's the first 5 of the constraints put upon us. The next constraint is that we only have 30,000 available. So 1,500 DTV. We write this out in this way because we're spending $1,500 for every daytime TV ad we run. Plus, for every evening TV ad we run, we're paying $3,000. And all of that added together, this sum product has to be less than or equal to 30,000 because that's our budget. Then we have to run at least 10 TV ads. So the DTV, daytime TV, and evening TV both have to be greater than or equal to 10. Next, at least 50,000 potential customers must be reached. So similar to this one. And if you're writing this out, just copy and paste these and change a couple of the numbers around, because it's going to save you a little bit of time. 50,000 customers reached would be 1,000 customers for every daytime TV, 2,000 for every evening TV, 1,500, 2,500, 300. That's the amount of customers you reach, and that has to be greater than or equal to 50,000. You can see here, less than or equal to, less than or equal to, greater than or equal to, greater than or equal to, and then another less than or equal to. I recommend highly that when you're writing these out, all of your less than or equal to, group them up. All of your greater than or equal to, group them up. Don't go back to less than or equal to again. Because what's going to happen if you do that is you have to have another set of constraints in the solver tool. Whereas if you had two of them, you could highlight this one, add, highlight this one. Okay, and you're done. By having that change directions again, you have to have a third set of constraints. So ideally, you set this up in a different order. But this is how all of the constraints can sort of be seen depending on how your spreadsheet's set up. But let's go back to the Excel file now. So we know that all of these constraints are formulated in this way. Let these letters equal this value, right? We want to maximize our exposure quality rating, whatever it was, yeah, subject to these constraints. So you've got all the ones we just went over right from the book. And then you've got the amount of budget available, television restrictions, and so on. And then finally, the last thing is going to be, they don't list it there, but again, you have to write out this non-negativity. And I touched on this in the lecture, but let's go over it again, what this non-negativity means. I can't run negative 100 evening ads to free up more money. I either run 0 or I run more than 0. So this non-negativity says that any one of these variables cannot be a negative number. It can be 0, but it has to be at least equal to. It can be greater than 0, but it has to be greater than or equal to 0. And you do not have to set this up in Excel. Excel has a check mark that you'll check when you open the solver tool. All right, so we're going to write in all of our parameters. We know that 1,000 customers reached for every one of these ads, 2,000 and so on. We now have the costs here. We have the availability. How many can we run of each of these per month? Exposure, quality per ad, the thing we're trying to target. Great. And then some additional information. We also have to, so these are the finite things. These are like the management constraints. They're telling you, oh, also, we're only going to give you 30,000. Also, you can only spend 18,000 of that on TV. Also, we want 10 TV ads at least. Also, you need to reach at least 50,000 people. Okay, great. These are known things. These are, management decisions, but they all go into your constraints file, because now you, as a person who's actually deciding how many to run, that's your decision variable. So that's why the number of each of these to run is your only decision variables out of all of these. So how many we're going to run, I don't know. And what I don't know, I put in 1 here because I'm just putting in a placeholder so that I can set up my formula. So we've got, oops, this should be, there we go, missed that one. So our maximize exposure should be yellow, because that's going to be our objective function. We want to maximize our exposure. And what we're going to have here under reach is going to be the sum product of however many ads we place as a sum product of the number of customers reached for each one of those ads. So we're going to have sum product, go ahead and lock it in this range, comma, customer reach. And then number of TV ads we run, well, the number of TV ads we run is going to be equal to, okay, so I don't need to lock that in. Number of TV ads we run is going to be equal to the number of daytime TV plus the number of evening TVs. So this one's going to be equal to daytime TV plus evening TV. So right now, we have to run at least 10. We're not running at least 10 so far. And here we've got our TV budget. So however much we spend on TV, we know that that needs to be equal to or less than the amount of $18,000. That's the most we're allowed to spend. So this one's going to be equal to the TV. Sorry, going to be equal to a sum product of the amount spent on TVs and the cost for each of those TV ads. Okay. And then the last thing we need to do on this side is going to be a sum product of our total budget. So this is budget for just TVs on the top line, and then budget for all the ads on the bottom line. So again, a sum product of how many ads I place, multiplied by the cost per ad, and then added together. So if I run one of each, I've got 6,000 of my 30,000 used already. And you can see on here, if you look at the amount of the cost on these, yeah, this reaches a lot of people, 90 people, 2,000 people, but it is costing a ton. It's costing 3,000 for each one of them. So I don't know that we're going to run many of these evening TV ads, probably. Okay, are there any other ones we need? I don't think so. Okay. Oh, there is another constraint right here, which is total number of ads. So each of these being less than this number. So we don't need to write it out separately down here because we're gonna just do that in the solver tool. All right, I'm with it now. So that's the setup. Oh, max exposure. Max exposure is going to be equal to a sum product of the amount that we end up at running and the exposure for each of those ads. There we go. All right, so now we should be able to run this tool in solver. So the objective right here, maximize the exposure, maximize the set, changing the variable cells. We can only change these ones. How many we're gonna run, and then let's see what we need to add. We're going to need to add a less than or equal to. So that's going to be all of the ads we place have to be less than or equal to the available number of each of those ads. Okay, that's one. Then we're going to change directions, and we're going to go to let's see here, right here. The amount we reach, we have to run at least 50,000 people have to be reached, and at least 10 TV ads have to be run. So this one, we're going to switch the direction to greater than or equal to, and then the right-hand side is going to be on this side. And then finally, we're going to switch directions one more time. And we're going to say that the TV budget and our full budget have to be less than or equal to the budget of each of those. All right. So that's all of our constraints. We've got this make unconstrained variables non-negative. So when I said you don't have to, in Excel, write out this non-negativity variable, it's because you just check that box. Don't uncheck that box. It's still set to simplex LP, so we're going to hit solve, and it found a solution. We hit OK, and we, hope it was the best solution. All right, so that is the TV ad one. Relax is the name of the development corporation. All right, Welty mutual fund problem. So in this problem, we're trying to maximize our total return on our investment. And we are given a rate of return of these amounts. We are told that we have a certain amount available. So let's see, this is on page 564. This is the investment portfolio selection. So these are the rates of return. These are given to us as percentages, but we need Excel to do the math on this. So we're going to put it in Excel as, so 7.3% is equal to 0.073. 10.3% is 0.103, and so on. So convert these to decimal places. And then we're told that neither the oil nor steel industry should get more than $50,000 of our money. The amount we put into government bonds should be at least 25% of whatever we put into steel industries. So there's two steel industries. The investment in Pacific Oil, the high return investment, cannot be more than 60% of all of the oil. So however much we put into both the oils, Pacific can't be more than 60% of that. So if I put $1,000 into it, I could put 600 in Pacific and 400 in Atlantic, but I couldn't put 700. That wouldn't work. We're going to run the entire $100,000. So in this case, they've run it as equals 100,000. I would still set it up as less than or equal to 100,000. I guess you wouldn't have to invest all of it potentially. The requirements that neither industry gets more than 50,000 are going to be equal to the total amount of. They use X1, X2. I went ahead and used A, P, N, H, and G on these instead of the X1, X2, X3, X4, X5s. Probably could have set it up with the X1s, but okay. Defining the decision variables, I set it up as their first letters. Maximize the profit, maximize the return on investment equal to 0.073 times X1 plus 0.103 times X2. So the amount of return for each one of those, for every dollar invested in each of those possibilities. The constraint that we spend all 100,000 is going to be equal to just all five of them added together. It has to be 100,000. The two oil industries kept to be less than or equal to 50,000. The two steel industries added together have to be less than or equal to 50,000. So this one is one of the times where we have just the variable on the left, and then we're gonna have a formula on the right hand side of the equation, just the way it's formulated. So however much we put in government bonds, that fifth one, has to be greater than 25% of the steel investment. So greater than 0.25 times the two steel industries added together. 25% of that, we have to be at least that much in government bonds. And then Pacific Oil has to be less than or equal to 60% of both of the two oil companies added together. All right, and then your non-negativity is just your five variables separated by a comma, and we're done. So here's what that looks like in Excel, except I put the letters A, P, M, H, G because they all were five different letter investment opportunities. Maximize those subject to these things. So equals, we got two less thans followed by a greater than followed by another less than, which I hate to see, but that's just the order they set it up. And so what are we going to invest? That's our decision. When that's our decision, I'm just going to put a 1 in for a stand-in. The total return is going to be equal to a sum product of whatever the contribution is for each of those variables, comma, the amount we actually invest. So if we invest $1 into 5 different industries, we've made 36 cents. Seems totally worth it. Funds invested. So that's going to be the total of all of our money, because that constraint was A plus P plus M plus H plus G. So that's just going to be the sum of these 5 things. Unused funds, we can't have, we need to spend them all. So funds available minus funds used. Right now we've got $99,995 unused. Funds invested. So we have oil is going to be Mountain Oil plus a Mountain Other Oil. Steel is going to be equal to the amount in Midwest Steel plus Hooper Steel. Pacific Oil. So this one was saying that this is the one where Pacific Oil has to be a certain amount, right? So on the left-hand side, it's just going to be equal to Pacific Oil. But then on the right-hand side, this was the 60%, so less than or equal to 60% of A plus P. So equal to 60%, which we have right here, times, open our parentheses, Atlantic oil plus Pacific oil. So right now it's not, we don't have a, oh no, we're still good. We're still less than or equal to 120. And then government bonds, the amount of government bonds invested, which is right here, government bonds, has to be greater than or equal to 25% of the two steel companies. So equals 25% of this steel plus this steel. All right, and we have our setup in Excel done. So we're going to go to Solver. Our objective is our maximize total return. Maximize is selected. The only thing we can change are these 5 things right here. What constraints do we have? All right, so the constraints we have in this case are going to be, we've got the first one is that the total amount invested has to be equal to $100,000. The next one we have available is that these 3 right here all have to be less than the maximum amount allowed. Hit add, and then this government bonds has to be greater than or equal to this constraint on the right hand side, and that should be all of it. Yeah, so it shows us 3 constraints because we were able to group all 3 of our greater thans together, and then our less than was on a separate line, our equals was on a separate line. Perfect. And then click solve, and we found a solution of $8,000, which, you know, hopefully matches what the book has. It does. Great. And all right, last but not least, we have the one that is set up just like your problem last week. So the formulation on this is a lot crazier, so let's talk about it. This formulation is a little bit different than the other ones. You're going to see let xij. What does that mean? Well, in this case, we've got origins and destinations. The origins are in Cleveland, Bedford, and New York. The destinations are in Boston, Chicago, missing an I, St. Louis, and Lexington. So those are our destinations. So instead of writing out Cleveland to Boston as one variable, Cleveland to Chicago as a second variable, Cleveland to St. Louis, Cleveland to Lexington, Bedford to Boston, every one of those, all 12 of those possible things, instead of writing out 12 different origin destination combinations as different variables, we can just write this, where I is the number of units shipped from origin I, and J is the number of units shipped to destination J. And then I equals 1, 2, 3 equals Cleveland, Bedford, York. And then J equals 1, 2, 3, 4 equals Boston, Chicago, St. Louis, Lexington. You might be asking, well, how are we going to have 1, 2, 3 here and 1, 2, 3, 4 here? So what the IJ is standing for is every time you see a number in the first position, in that I position, it's the origin. If you see whatever number you see second is the destination. So you can have 1, 1, and that means whatever is listed as the first one. So under I, 1 is Cleveland. So we know that, and then under J, 1 is Boston. So if I see X 1, 1, I know that it means from the first origin to the first destination. If I see X 2, 3, it's going to be Bedford because it's the second origin to St. Louis, which is the third destination, and so on. 3, 4 would be York to Lexington because it's the third origin, 1, 2, 3, fourth destination. So that's how Xij works. It's still long, but it's less than writing out let X11 equal the number shipped from Cleveland to Boston. Let X12 equal the number shipped from, and writing 12 lines of writing. So this is a shortcut for that in a transportation type problem. Transportation, transshipment, both have this Xij thing. All right, our minimized problem is long because there are 12 costs. This is a cost saving. In transportation problems, generally you want to minimize your total costs. So we are given a cost to ship from Cleveland to Boston. It's $3 per unit. We're given from York to St. Louis is $4 a unit. We're given a series of costs depending on where we ship from and where it's shipped to. We're also told that in Cleveland, we have 5,000 available. In Bedford, we have 6,000 available. In New York, we have 2,500 available. And then Boston, Chicago, St. Louis, and Lexington, they have these sales demands. Maybe they're pre-sales, maybe they're just forecasting or whatever, but this is how many units need to be shipped to these locations. So that's what this whole setup is. And the minimized thing is going to be our costs. So the first thing you do is write the value here for the cost, 3, and then X11 is Cleveland to Boston, okay? So that's what 3X11 is, plus 2 X12 because it's Cleveland and Chicago, 7 X13 because it's Cleveland and St. Louis, the first one to the third one, 6 X14, and so on until we get all 12 of the possible combinations listed. And whatever that number ends up coming out to, that we want that number to be as small as it could possibly get. This total cost, we want it to be small as possible. Then we have 2 different types of constraints in a transportation problem. We've got supply constraints and demand constraints. So our supply, the amount we ship from X11, right, which is, if you look at this first line, it's everyone is X11, X12, X13, X14, because 1 is the first number. It means it's shipped out of Cleveland because Cleveland is the very first origin. So all 4 of those locations that Cleveland can ship to all get added on one line, and the amount that it ships has to be less than or equal to 5,000 because we only have 5,000 available. Same thing's true here. And a nice shortcut when you're writing these out is if you write this first line, copy and paste it 2 more times. Change the first number from 1 to a 2 on each of these. And now it's everything shipped from Bedford to the same 4 locations. Now it's everything shipped from York to the same 4 locations. You just change 1 number on each of them. And you change Cleveland supply, you just change it Cleveland to the word Bedford, Bedford to York. Save you a little bit of time. Demand constraints. So you can see the supplies supply 4 places, but there's only 3 of them. So there's 3 supplies. There should be 3 constraints here. There's 4 destinations, 1, 2, 3, 4. There should be 4 demand constraints. And the demand has to be met. So we got to ship. Oops, I've got the wrong. I just realized I did copy and paste. I told you to copy and paste, but I didn't change the supply. I didn't change the demand. So that's my fault. Now you get to, I'm not gonna bail myself out by pausing and cutting this piece out. If you're gonna copy and paste, you can make sure you change everything. All right, so the demand constraint, Boston needs 6,000. The amount that Boston gets from all the shipments is gonna be everything that ends in a 1, because Boston, as the second number, is everything that ends in a 1. It's the first destination. So X11, 21, and 31 is Cleveland to Boston, Bedford to Boston, York to Boston. And then X12, 22, and 32 are Cleveland to Chicago, Bedford to Chicago, York to Chicago. So all of those have to equal the demand from each of these locations. And then finally, we can just write Xij greater than or equal to 0 as our non-negativity. So here is why I had you set up this problem with equals sum on each of these nodes last week, just to give you a little sneak peek. equals sum of this row, because this is everything shipped from Cleveland, all the locations, everything shipped from Boston or to Boston. It's going to end up here. And then our total cost is going to be equal to a sum product of all the costs and all of the amount shipped, which right now is nothing. We're not shipping anything yet. The solver tool will solve it. Usually I do put in a stand-in just to see if it's working. So let's go ahead and keep that trend up. We should see 4 on each of these because there's 4 cells. We should see 3 on each of these because there's 3 cells. And then the sum product should be equal to whatever the sum is of all of these. And if I highlight them, I can look at the bottom right and see the sum here. So I know it's working. Now I just need to run up to the solver tool, and we want to do the objective function right here, total cost, but we want to minimize that by changing all of these cells, all the amount shipped, and we're going to add in our constraints. So our constraints are going to be 2 things. One, we know that we'll do these ones first. All of these sums, the amount that I shipped each of these spots has to be equal to the demand right here. Add, and then all of these ones have to be less than or equal to the supply right here. So I can't ship more than I have available, and I have to get the demand met. I hit OK. I hit solve. It found a feasible solution. It says that 39,500 is the least money I can spend, and this is the answer. There are actually 2 answers on this problem, I believe. So it's possible that if you were running this practice, you would get the other possible answer. That happens sometimes, that there's just 2 feasible solutions that are also the optimal solution. And that's fine. I have both of the possible solutions listed. So on the real problem, if that were to happen, I've got both of them in my answer key in case it just randomly selects the other one. So that is it. I expect I might have to rewatch a few parts of that, but if you have questions, please let me know. And the good news is this is the last problem set of the class. So thanks everyone. Great job keeping with it.